Welcome back to Lecture 8. In this second part of Lecture 8, we're going to examine the mathematics of the Reynolds Averaged Navier Stokes or RANS approach to turbulence modelling. Remember that the RANS approach breaks down flow fields such as velocity and pressure into steady components and fluctuating components. Firstly, we'll remind ourselves that when we use the RANS approach, we introduce an extra unknown into the Navier Stokes equations called the Reynolds stress. Now, this additional term can either be solved directly with its own transport equation, or it can be linked to properties such as eddy viscosity, turbulent kinetic energy, and velocity gradients using something called the Boussinesq hypothesis. Both of these approaches are very good examples of modelled physics, the testing of which, if you recall, was step 6 of the CFD validation workflow. When the Boussinesq hypothesis is used, we need an additional equation to solve for the Reynolds stress. This additional equation is called a closure model. We'll introduce two closure models, k-epsilon and k-omega. We'll see how these are mathematically formulated, and then we'll see how they're used in a practical context. Now, let's do a little bit of a recap to start with. Now, if you recall your previous fluid mechanics course, you formulated the Navier Stokes equations with fluctuating and average components of velocity and pressure. Now, we're not going to go through that derivation here. This should be something you should go and revise if you're unfamiliar with it, but the key result was this. What you have is the Navier Stokes equations written as I've put them here on the whiteboard, where the dominant components are the steady components, the ones with a bar across. And so you'll see most of the components here are either U bar or P bar. However, there is one term on the right-hand side of this equation that involves the time fluctuating component U dashed. See on the right-hand side you've got minus rho U dashed dot grad U dashed. That component comes, of course, from the left-hand side. It actually forms as part of the convection term, and this is a term that gives us problems. Now, what we can do is we can take that term, rho u dashed dot grad u dashed, operate on it using the chain rule. Also, remember that we're dealing, for the purposes of this course, with incompressible flows, so we'll also add continuity into the equation, if you'll excuse the pun, so that del dot u equals 0. And we arrive at this equation that I've put on the board, which on the right-hand side has a divergence of a set of stresses. Now, if we examine that in a little bit more detail, we have the shear stress tau, which we know we can link to the material property of viscosity and the shear rate tensor. And we have this other term here which involves the time fluctuating components, and this is the extra unknown, and this is called the Reynolds stress tensor. Now, if you think back to your previous course, what you then did was to say operating in 3 dimensions is too hard to do analytically for most cases, so we'll drop it into 1 dimension. And when we drop it into 1 dimension, we can rewrite that group of stresses as having my shear stress, tau equals mu du dy, written with respect to the steady part of the flow, u bar. And then we've got this random fluctuating component, rho u dashed v dashed. What do we do with that fluctuating component? Well, what you did was to introduce a simple closure model, Prandtl's mixing length model, which works in 1 dimension. And what you ended up with was a result for stress which had 2 components to it. It had a viscous component and it has an eddy-based component. And if you look at how this has been written on the whiteboard here in front of you, you'll see that the fluid viscosity has now been written in terms of a kinematic viscosity, orders units meters squared per second, which also means that eddy viscosity is meters squared per second in terms of its dimensions. And so, if you recall how you operated on heat transport and mass transport, you ended up with very, very similar types of expressions, which also involved this eddy viscosity epsilon. And when you think about heat transfer, rather than looking at tau yx, you will be working out a turbulent heat flux instead. The key problem then is, well, how do you work out epsilon? And this is where you needed another bit of modelling, and you use non-dimensional velocity profiles. You looked at the parameters of velocity and distance. You found parameters with which you could use to non-dimensionalize them, typically involving a shear stress of some sort, and then used experimental data to plot out how non-dimensional velocity varied with non-dimensional distance, and you ended up with something like, for example, von Karman's universal velocity profile. You can substitute the results of von Karman into this stress expression here, which also gives you the ability to work out how epsilon, my eddy viscosity, relates to velocity gradients. And it's that relationship between epsilon and velocity gradient that allowed you to estimate epsilon, which in turn allows you to estimate things such as the stress, or the turbulent heat flux, or the turbulent mass flux. Now, when we're thinking of computational fluid dynamics, we need something that works in 3 dimensions and not just 1 dimension. We're going to follow a similar approach to Prandtl in terms of having an extra set of equations, but they need to be more complex and rigorous. So, in 3 dimensions, we need to close this Reynolds stress term, this rho u-I u-j term here on the right hand side of the time averaged Navier Stokes equations. Now, there's one of 2 ways we can do this. Firstly, what we can do is to use a better eddy viscosity model compared to Prandtl. We can relate rho u-I u-j to properties of the flow that are known, hence calculate that, and hence relate that to the overall momentum balance. And we'll have a look at how we do this in a minute. Another approach is to say, well, look, what we've got is a stress term here. We can define a transport equation for this. And if we define a transport equation for this, we don't have to worry about estimating eddy viscosities, and we can just solve directly for Reynolds stress. So we'll have a look at that in a few slides' time. So let's start by thinking about this first approach, using a better eddy viscosity model. So there's something called the Boussinesq hypothesis. This relates the Reynolds stress to an eddy viscosity, to a velocity gradient, and to turbulent kinetic energy. Now, the Boussinesq hypothesis can be written as I've written on the board here. Now, at first sight, this looks like a bewildering amount of terms, and they're written in summation convention terms rather than the tensorial terms you might be familiar with already. We'll go through this term by term to see how this works. So, let's have a look first of all at the dimensions. We need to have our mental model to make sure that when we calculate terms that we always have the right terms in the equation. We're dealing with stresses in Reynolds stress, and so all the terms have fundamental dimensions of Pascal. The first term in these parentheses is gamma dot bar ij. Gamma dot bar ij is simply my rate of strain tensor. You might have seen it on previous courses, such as a rheology course, written as bold gamma dot. And this is grad v plus grad v transpose. And I've written that tensor out in full for Cartesian coordinates. They're on the board highlighted in purple. You have on the diagonal your extensional components, and you have on the off diagonal your shear components. So gamma dot bar ij is simply your rate of strain tensor, which is a quantity you should hopefully be familiar with. Let's look at this second term. Now, 2/3 partial du bar k by dx k delta ij. Delta ij is a delta function. This is a function that equals 0 when I doesn't equal j, and equals 1 when I equals j. And we need to know what I and j are. We also need to know what k is in that partial derivative. The way I like to think of this, as someone who's interested in computer programming, are basically for loops. You've got 3 nested for loops here. For I equals 1 to 3, for j equals 1 to 3, and for k equals 1 to 3, one nested inside the other. And what you do is you just execute these loops to start with. So you count up at your innermost loop first, that's k, and you just sum terms. So let's look at that partial derivative, du bar k by dxk. Well, if I count from k equals 1 to 3, for each individual value of k, that's each of the individual components of the vector u. And so that's going to be an x direction velocity, a y direction velocity, and a z direction velocity. For the gradient operator, which is a d by dxk bit, then for every single value of k, for k equals 1, you've got the x direction, d by dx. For k equals 2, you've got the y direction, d by dy. And for k equals 3, you've got the z direction, d by dz, on the assumption that you've got a Cartesian coordinate system. So thinking about that du bar k by dxk term, as we go through that innermost loop, if you like, what we're doing is just adding those partial derivatives of velocity with respect to distance together. So it's du by dx plus dv by dy plus dw by dz, which is simply a statement of continuity. So at each inner loop, you're evaluating continuity. Now we can see from the result that the continuity equation only appears on the matrix diagonal. That's where delta ij comes into play, because what you're doing is you're multiplying that continuity expression that you evaluate in that inner loop by a value that delta ij takes. And so if we imagine we start our counting when I equals 1, when j equals 1 and k equals 1, we count up from k equals 1 to 3 in that inner loop, and that's multiplied by whatever value delta takes when I equals 1 and j equals 1. And we're defining delta ij to be equal to 0 when I doesn't equal j, and to be 1 when I does equal j. And so when I equals j, we have continuity. And so when I equals 1 and j equals 1, that's the 1, 1 position in our tensor, which is the top left-hand bit. If we go right to 1 unit, where we've got that 0, that's when I equals 1, j equals 2, and then we count up in k and form our continuity equation. But because 1 doesn't equal 2, delta ij equals 0. And so if we think about this equivalence between the summation convention here and for loops, then we can hopefully have again a little way that we can calculate the contents of these tensors using summation convention. And I've purposely used summation convention here in order to explain it to you. So what we have is effectively, from the second term in this Boussinesq hypothesis, is continuity placed on a diagonal of a matrix. And of course, if we've got an incompressible fluid, that equals 0. And so for incompressible fluids, we can ignore that second term. This third term, if we look at it, is 2/3 rho k times delta ij. So delta ij, we know, is our delta function, which is 1 when I equals j. K here is not part of our summation convention notation. It's simply my turbulent kinetic energy, k. And so what that says is that I have 2/3 rho k on the diagonal of the matrix, which is what I've written out there. So this is what the Boussinesq hypothesis states. We can relate my Reynolds stress to my shear rate tensor, to a statement of continuity when that is placed on the diagonal of a matrix, and to another matrix which relates to turbulent kinetic energy k. So that's Reynolds stress in 3D. Now how do we actually calculate these values? Because if we look at Reynolds stress tau r, we've got mu t. Mu t here is my eddy viscosity, so I need to be able to work that out. Delta bar ij, that is my strain rate tensor in terms of steady velocities. I know what that is. Hopefully we're dealing with an incompressible fluid, so we don't have to worry about that continuity term, but if we do have to worry about that continuity term, it's posed in terms of steady velocities, which again is something I will know. If we look at the final term, we've got turbulent kinetic energy appearing k, so we need to be able to work that out. And so we've got eddy viscosity and turbulent kinetic energy as two additional terms now that appear in this Reynolds stress tensor. So this is why we need a turbulence model. We need to be able to calculate k and mu t. Let's have a look at one of the most commonly used turbulence models, k-epsilon. Now, it defines eddy viscosity mu t in terms of turbulent kinetic energy k and this dissipation factor epsilon. And there's an empirical constant here, C1. You'll see there are 6 empirical constants within k-epsilon. So this still needs a means of calculating k and a means of calculating epsilon, hence the name of the model. What we do is we have 2 transport equations. We have a transport equation for k. Now k is a scalar quantity, and there's the transport equation for it. And we can see, if we look at that transport equation, it involves eddy viscosity mu t. It involves epsilon. It involves turbulent kinetic energy within one of the terms, so it's implicit. It's also got the strain rate tensor written there. We've got also the fluid viscosity written there. So our unknowns in this equation are going to be epsilon, which is something that we need to calculate. It's calculating k for us, so that's fine. And mu t, of course, we can relate to k and epsilon, so we can substitute that expression for mu t into that transport equation. We need a transport equation, therefore, for epsilon, and that I've now written on the board for you. And we can see that both in the transport equation for k and the transport equation for epsilon, we've got further empirical constants. For the k transport equation, we've got C2. In the epsilon transport equation, we've got C3, C4, and C5. So, if we look at the terms in both of these equations, we'll see they're coupled together because we're solving for k and epsilon and k both appear within these transport equations as well. So, those two transport equations need to be solved simultaneously with the time averaged Navier Stokes equations, which I've now written on the board for you. So if you have a code, or can write a code, that can solve all three of these sets of transport equations in parallel, along with the appropriate application of the numerical constants C1 through to C5, then you should be able to solve for a turbulent flow using the k-epsilon closure model. Now there's a few subtleties about k-epsilon that we need to introduce. The key subtlety is that k-epsilon cannot resolve the behaviour of fluid flow close to walls. And what we mean by close depends on a type of approximation that we use. Now, let's think about flow next to walls for a second. In a previous fluid mechanics course, you will have seen that up to 3 zones can exist near a wall. And these zones were defined in the non-dimensional world. So I'm going to plot a sketch of a graph. The axes are going to be logarithmic, and u plus is a non-dimensional velocity. So it's my real velocity divided by a non-dimensionalizing term, and that non-dimensionalizing term typically involved a shear stress and a collection of other terms. Y plus is non-dimensional distance away from the wall. Some people get confused in cylindrical coordinates thinking that it is out from the core of the flow. What we're interested in is physics at the wall, so Y plus is distance away from a wall. And again, this is non-dimensionalized with parameters that we can take from the flow. There's shear stresses and viscosities wrapped up in that. So, as we look near the wall, there is a linear region. It's a curve on these axes because don't forget this sketch are logarithmic axes. And near the wall, very close to the wall, you have the non-dimensional velocity u plus equal to the non-dimensional distance away from the wall y plus. As we look quite a long way away from the wall, we find a different regime of behaviour. We find a logarithmic regime of behaviour where the non-dimensional velocity u plus goes roughly as 2.5 log the non-dimensional distance y plus 5.5. Now we can see here that there's a whopping great discontinuity between these two curves, and the u plus equals y plus regime we call the viscous sublayer. The u plus is 2.5 log y plus 5.5 we call the turbulent core. But we need to join these two things together to somehow get rid of this discontinuity, and we introduce something called a buffer layer to do that. And we effectively try and draw a reasonable line of best fit between these two descriptions. And the line of best fit typically goes as u plus, non-dimensional velocity, is 5 log y plus minus 3.05. So hopefully that will ring a few bells for you for courses that you've sat in the past. The key message here is that there is behaviour going on at the wall that we need to capture in more detail than we can using k-epsilon. So, depending on how we describe fluid flow near the wall, we'll find typically that k-epsilon is valid in the turbulent core of the flow, but we need another piece of modelled physics to figure out what's going on in the buffer layer and in the viscous sublayer. Now, these different pieces of physics are called wall functions. What wall functions do is describe in a semi-empirical way what happens to non-dimensional velocity, to turbulent kinetic energy, to dissipation rate and to Reynolds stress as you get close to a wall, because k-epsilon and the set of transport equations that describe k-epsilon can't resolve those quantities close to a wall. There's actually a mathematical divergence there. And so what we find is that there are many different types of empirical description of wall function that can be used to describe the variation of these properties as a function of distance away from a wall. What this means from a practical sense, if you're modelling turbulent flows, is you need to design your mesh very carefully. In the final part of this lecture, I will give you some mesh design hints, but there's two things really that you should be thinking about here. If you have something called a standard wall function or a non-equilibrium wall function, these are two different classes of wall physics that describes the variation of U plus K and epsilon and tau r near a wall, then the advice typically is that the centroid of the cell nearest the wall should be located within 30 to 300 units of non-dimensional distance away from that wall. The closer you can get the centroid of that cell to y plus equals 30, typically the better. There's another family of wall physics called enhanced wall treatments. Now, with enhanced wall treatments, you can take k-epsilon a little bit closer, and your mesh should therefore reflect that. And the centroid of the mesh cell nearest the wall should be around non-dimensional distance y plus is 1-ish. And you should try and put at least 10 mesh cells in the viscosity affected region, the viscous sublayer, near the wall. So you need to design your mesh specific to the type of approximate wall physics that you're using when you use the k-epsilon model. So the major take-home is that k-epsilon cannot be used up to the wall. You need to introduce something else called a wall function, and that your mesh design should reflect the type of wall function that you specify. Again, I'll give you an example of this in the final part of this lecture. Now, in terms of advice from the authors of Fluent, they say, look, standard and non-equilibrium wall functions are good for high Reynolds number flows, if Reynolds number is over about 10 to the 6. If, however, you've got slower flows, the enhanced wall treatment may be a little bit better. So the type of wall treatment that you use depends very heavily on the type of flow that you've got. We haven't got time in an 8-lecture course to go any further into this subject, but if you look in the literature, there's lots of good advice and additional information as to what's actually going on with wall treatment models and actually how you use them. Now, of course, it would be ideal if we didn't have to do this. What would be far better is if we had a closure model that allowed us to resolve right up to the wall. And indeed, such a closure model does exist. In fact, there's a number of closure models that exist, but the one I'm going to talk about is a close relative of k-epsilon, which is called k-omega. And k-omega describes turbulent kinetic energy k and a specific dissipation rate, omega. I've put on the whiteboard there a statement of Reynolds stress again. That's our starting point. Remember, what we're trying to do with these closure models is evaluate eddy viscosity, mu t, and turbulent kinetic energy, k. And the first step that we took previously with k-epsilon was to define what mu t was equal to. So we're going to do the same here with k-omega. And mu t now is related to k, as it was before, my turbulent kinetic energy, and now my specific dissipation rate, omega. And again, there's an empirical constant in here, C6. What we then have, as before, are a set of transport equations. One that describes k, one that describes omega, and then one that describes the steady flow velocity. If we look at this set of transport equations, they are actually very similar in form to k-epsilon. There are a few minor changes, and I've highlighted those changes in blue, but otherwise we'll see effectively we've got a very similar thing that we're trying to achieve. We've got a transport equation for k that involves omega and k, and mu t we can again substitute k and omega for. We've got a transport equation for omega, which again involves omega and k. And then we have a transport equation for momentum, which involves my mu t and k. And so again, if we can solve all these equations in parallel on a suitable finite volume mesh, then we should be able to describe our turbulent flow. We have a set of empirical constants that I've given here, and again, all this is an excellent example of modelled physics. So think about that 6th step in the validation process, which is checking your modelled physics. What impact does C1 through to C6 have on the prediction of your flow field? Very little impact or a massive impact? We'll discuss that more later. So, k-omega is valid over all distances, and so we don't have to worry about wall treatments, but what we do have to do is to think about how we place mesh cells. So when we think about designing a mesh for the k-omega closure model, we need to put a very fine mesh near the wall, and so we're looking to have about 10 mesh cells in the viscosity affected region. So we'll see how we do that and an example of that in a minute. Now, we've introduced the Boussinesq hypothesis, and the whole idea of the Boussinesq hypothesis was say, you've got Reynolds stress, let's approximate Reynolds stress to some quantities such as kinetic energy, dissipation rate and turbulent kinetic energy, and then write transport equations for those quantities. And we did so using k-epsilon and k-omega. The other approach is to not use the Boussinesq hypothesis. The other approach is to say, let's just directly define a transport equation for Reynolds stress. Let's forget about eddy viscosity models. And what you can write is a transport equation of the following structure. Tau r here, if you remember, is my Reynolds stress tensor. So this is a transport equation now for a tensorial quantity, not a vector quantity. And we have on the right-hand side things such as P, your stress source terms, F, your rotation source terms, D, your turbulent diffusion source terms, phi, your pressure strains, and epsilon, your dissipation. And of course, each of these terms has to have a physics model underpinning it. Now, describing Reynolds stress in this way is actually more physically sound than making an eddy viscosity approximation. However, what you have are a lot of empirical models underlying all these different source terms and dissipation rates. And so, first of all, you've got a lot more model physics to deal with. And again, there's this whole question when you come to validate is how well this model physics is doing. But also, you've got a massive transport equation to solve here that's actually transporting a tensorial quantity, which means that from a computational standpoint, you're going to need more CPU time, significantly more memory, and convergence may become quite a challenge. However, Reynolds stress closure is very good for complex 3D flows involving rotation, and may be your go-to model of choice for those, but probably only once you've tried to see if some of the simpler methods using the Boussinesq hypothesis, such as k-epsilon and k-omega, are sufficient for purpose. And this really does highlight the importance yet again of figuring out what it is you're trying to solve and what is fit for your purpose. Don't forget, more than likely you're using these simulation tools for engineering design, not for the detailed understanding of fluid physics. And so figure out what level of detail is appropriate to solve your problem. Let's go through a few key points. We've looked at the Reynolds Averaged Navier Stokes approach, and we've seen that we can break a flow down into steady components and fluctuating components. What this means is that there's an additional term that appears in the time average Navier Stokes, which is the Reynolds stress tensor. This extra term, this Reynolds stress tensor, needs additional equations to be solved. So you have the Boussinesq hypothesis, which bridges the Reynolds stress to eddy viscosity models. And then you have closure models, such as k-epsilon or k-omega, that calculate the various terms within the Boussinesq hypothesis. We've seen the k-epsilon model defines transport equations for k and for epsilon, but can't calculate right down to a wall. We've seen the k-omega closure model, which can calculate right down to a wall. The mesh design for both k-epsilon and k-omega is critical in order to get a converged simulation. We've also seen that there's a different approach, which is to ignore the Boussinesq hypothesis and just to define a transport equation for Reynolds stress. We've seen that this involves a lot of empirical model physics, and it involves the transport of a tensor quantity, and so the computational overhead is greater, with also in a greater emphasis on higher computational resource.